Yeah, I think I left that last time on that, so it's probably, yeah, I think it's mine. Yeah, thanks, Berton. Okay, how's everybody doing? Hey, thanks for somebody answering, that's great. And I'm glad that you're doing pretty good. Whoever said it. Great. That's good. Who is done with the homework? Yeah, nice, done. Who is not done with the homework? Who has a long ways to go? All right. Well, it's due tomorrow, 11:59 p.m. So, how many hours is that left? At least 24.
I had a question on how you grade it. I found a couple like miscellaneous print statements in mine. Would those mess up the automated?
No. Nope.
Kind of like similar question, but do you care that much about like formatting, like using those two?
No. Good questions. Yeah.
Does it have to run in a certain amount of time? Like if our
No, because you're going to turn in it already run. That's critical. Like it's got to have the output in the cells. Like save that. Yeah.
And you.
I mean, if it's not there, we'll rerun it. But if it doesn't run, then that's just that's how it's going to be. So you be in charge of whether or not it runs. Okay. Don't leave us in charge. Is there a question over here?
I was going to say, when you download, I just like downloaded the type file after that.
Yeah, it saves all the output. Yeah, if you didn't like do anything clever like remove out cell output, that's like that's an option, but you don't want to do that. Yeah, just leave it all in there. It'll be fine. Yeah, cool. Great. If you have more questions like that, that's great. I'll be sticking around for a little bit after class to do my office hours, and I believe there still is one more office hour on Friday from one of the TAs. I can't remember who, but I think there's a Friday office hour. Is that right, Gernov? Arnav has his, yeah. Cool. All right. Well, let's get going. There were a few slides left from Tuesday that I didn't finish. It'll take us a couple of minutes, and we'll get on to Lecture-8. So this is where I finished last time. So we were talking about convolutional layers, convolutional operations in neural networks, and we've been talking about these filter sizes, and it's just as good to have a 1-by-1 convolutional layer. So the filter is just 1 by 1, meaning it's just like a column. Whose depth, still the same thing, depth of the output feature map, but it's just doesn't have any spatial extent. What do you suppose those would be useful for? They show up all the time, by the way. They're in all modern neural networks, well, convolutional neural networks. Why do you think we would even do that? It's actually right here in the little words. So just read it and then you can tell me. No. I mean, one of the things it's used for is to simply change the number of filters in your, or the depth of your output feature map. Still a learned, right? There's still parameters there to be learned, but in a very computationally efficient way, right? As the filters get larger, the computational cost of that layer gets larger, and that's one of the things you're trying to do is avoid computational cost with introducing this inductive bias of the convolution operation itself. And so when you get these really deep layers, you actually there are times when you want to do this, when you want to so like one of the most well-known kind of like famous convolutional networks is a residual network or ResNet. This is a key component of these blocks as you get down into as you get deep into this network is you literally take large feature map, like large in the sense of depth, you make it smaller with 1x1 convolutions, then you do like 3x3 convolutions, and then you expand back out, and so that you're back out to the original size. So it's a way to think of it as kind of like factoring your operations in some sense. So it's a bit of a shortcut. It does reduce the capacity slightly, but in general these are really these add a lot to the networks and allow them to become quite deep. So 1x1s are used all the time. They seem kind of weird, but they're actually not weird. They're very useful. So like just to say it concretely for this example, a 1x1 filter here would be of size 1x1x64, right? And then if I'm going to get a feature map of depth 32, then I have 32 of those. So it's exactly the same story as before, just they're 1x1. So don't get freaked out by them; they're all over the place. Yeah, because I'm a little bit behind. I'm not going to go through this too much, except to say the following: that one way you can think. Let's see. Yeah. One really useful way to think about convolutional network or stacked convolutional layers is this idea of the receptive field of any neuron in a feature map. So let's say I have this feature map. I'm focused on one of the neurons there, so it's one of these activations. Okay, so like the question you're asking yourself in a receptive field is, if I go back a layer, which neurons there, which activations there contributed to that value? And when you go back one layer, it's pretty simple to understand. But you can kind of keep doing this, go back further and further and further. You can ask like, what's the size of the receptive field, for a neuron in this layer, all the way back in the original image. And it's actually quite easy to figure that out if you just kind of have standard convolutional layer stacked with just activations in between. Even if you have like a pooling layer, that makes it kind of easy. However, when we get into like things like ResNets or dense nets that start to kind of mix earlier outputs with like the current output, we'll get there. You'll see it. What I mean. Then it starts to become a bit harder to work out in general. But this, it's an interesting concept to think about. What is the receptive field? What contributes to that value? And it can, it can vary. Until you're very deep in the network, you'll find that only a portion of the image is contributing to that, right? And so, one of the ideas of a convolutional layer is you're trying to like integrate you've introduced this inductive bias, which is like you're just focusing on small portions of the image, but you're hoping for the depth to kind of integrate those. And so, if you want to ensure that you're integrating all the information into your activations, then you need to make sure that your receptive field is the size of the entire image. So it's kind of one of those things to think about. I'm gonna keep skipping through here. Fully connected layers. We looked at this before. I think I mentioned this already. That, anyways, the point of this, the point here was just to say, like, you have the same notion with fully connected layers of receptive fields. It's just that, like, it's the whole input. In a fully connected layer, the entire input in one layer is the receptive field because everything's fully connected. All right, pooling layers. We haven't said much about them. I'll say something about them here. They're fairly simple. They're the preferred way. At least they were the preferred way of reducing the spatial complexity or the spatial extent of feature maps. So remember how we talked about padding last time, and if we add the appropriate size padding, and if we're just doing stride 1 convolutional layers, then the spatial extent of the output, the feature map, will be the same as the input, right? We'll have started with a filter whose center is in, like, one of the corners, and then we'll kind of work our way along the borders and work our way throughout the middle. So basically we have, for every single pixel, we'll have, that'll have been the center of every pixel in the input, that'll have been the center of the filter, and that will give us a corresponding pixel in the output in the feature map. So that's good. It's kind of like just kind of parsimonious. It's kind of like makes it simple to think about these things. That the convolutional operation itself is not doing any spatial reduction. If you do, of course, like stride 2 or more, that is going to reduce it. And so, like, that is another way that a preferred way of reducing the spatial extent. But another one that was popular, especially just early on, you'll see it in all the early convolutional networks, in the deep learning era, early in the deep learning era, so 10 years ago, is this pooling. And the idea of pooling is that we are going to take we're going to define the size. You can think of it again as kind of like a filter size. We're going to define some kind of size of our pools, and we're going to look at all of the values in that pool, and we're going to replace it with a value. We're going to replace it with another value. So that's how we reduce the spatial extent. Is like in this example, if we have 2 by 2 pools. We don't think about. I mean, there's no striding, but typically, we do these so that these are kind of like mutually exclusive pools. You don't have to do it that way, but it's typical. You say, okay, we have these 2 by 2 pools. Let's just choose a way of picking a number basically that represents what's going on in that pool. So in this example, this is max pooling. So in each of the pools, we just look and we see which value is the largest. And now we replace that 2 by 2 pool with a single value. So you can see that that's a reduction of the spatial extent by a factor of 2, in both directions, in the height and the depth, or in the length. Yeah, it's as simple as that. You can do other things too, like average pooling. You can average all of those. You can do min pooling. You can do all kinds of things. So max pooling. Let's think about that for a second. What is max? How would you justify choosing the max value within a pool? Why might you do that? Yep.
If they're all pretty similar, like if you have a bland color in your little square,
Mm-hmm.
then maybe the maximum is like, okay, yeah.
So in that case, like the maximum might be like the average, right? Like those would be about the same. So we could have just chosen the average. But why would we choose the maximum instead of the average? Let's just pose it that way. So it's kind of, well, take your example and then change it, yeah.
That might give you like a larger gradient.
Okay.
Like that propagation or something.
Mm-hmm. Yeah. Okay, good. So, like, take these ideas and kind of put them together. So, yes, if you just kind of had like you're saying, kind of bland or like kind of a uniform coloring in an area, your pool, the values in your pool probably all ought to be about the same, right? That's sort of uninteresting. Whether you choose max or average or min, you're going to get the same value. why might you do max? Well, remember what we're doing here is that, we have we've got these dot products all the way through, and these dot products represent alignment, and very large positive values mean alignment with with that filter. And then, we kind of keep composing that. So large values represent like a large response or a greater alignment with that filter in that region of the input. So if we do max pooling, we are getting, we're replacing that pool with the largest response, within that pool. So that seems good because we kind of want to preserve this, right? We want to preserve these this great alignment. This tends to be the signal that we want to be learning is like alignment with filters, right? So it's this combination of learning a filter and then that signal gets propagated through greatest alignment. So choosing max actually makes a lot of sense in that respect, that we're preserving when we do this kind of loss of information, right? When we replace a 2x2 pool with a single value, we're losing some information, but we're kind of preserving like the greatest response, and so that tends to be the most important in learning. It tends to it can lead to greater gradient signal, mainly because if we have a bunch of ReLUs, like that's going to these will be preserved, these won't be shut down to zeros and things like that. So anyways, that's a little bit of a justification of why you might want to do max. Now, turns out if you do max or average, it's kind of all works out. Like it doesn't. It's like one of those things that there's not much difference between them, except for every once in a while something weird happens and it is. But in general, it's like it's not. And one of the other interpretations of this is for pooling and in particular max pooling is this idea that remember that the inductive bias of convolutional layers is that we only care about correlations within small spatial extents, and we integrate that up. One of the other things I haven't explicitly said, I don't think, or maybe I did, but haven't spent a lot of time on it, is that this filter that we're learning is translationally invariant, right? So meaning that I can learn that filter once and I can apply it all over the image, right? So like in a fully connected layer, if you think about a small 3x3 filter, I might have to learn that filter over and over and over again if I'm doing fully connected. Like I might have to learn all the combinations of 3x3 filters to be able to do what I'm doing with a convolutional layer with far fewer parameters. So I have this idea of like the filters kind of space is like translation invariant. I can apply it here and I can apply it down here, and it's all it's extracting the same kind of information in a very efficient way, and it's making it's basically making like the network. It's allowing the network to be like insensitive to where exactly that particular pattern is showing up. Right? Like remember how we were looking at, I don't have this picture right now, but remember looking at KNN, and we talked about like the reasons why it was bad, and like if you just took an image and you shifted it a couple of pixels over, like to the right or up, then all of a sudden like that was the distance between that and like the original unshifted image was large, right? Because we were looking at the values at individual pixels. Convolutional layers don't have that property, right? Like if what we're trying to do is recognize that face, then whether or not that face is like in the bottom left-hand quarter or the top right-hand quarter, like we have a chance of learning it with these filters. And max pooling is a way of sort of extending that just a little bit to like within the size of your filters to not be so sensitive to exactly where the response is, but just that the response needs to kind of be nearby in that part of the image. And so when you think about like something that's detecting some edges here and here and here and here, you don't within a couple of pixels maybe it doesn't matter exactly how they're arranged. You just that they're there, and like this kind of operation sort of allows that to be preserved. And then as you integrate that up, maybe it's like, oh wow, this is like the texture of cat fur or something like that, and now I know I have a cat. So anyways, this allowing for this sort of additional insensitivity to the exact values of the of your input is also a benefit for that you get from pooling. Yeah.
So do you do that only to be insensitive, or is it also to shrink down your
Yeah,
data to 5?
it's both. It's
Okay.
both. Yeah, you want to shrink them down because that allow you're trying to integrate all the signal, and so you don't really want there to be a lot of spatial signal. Like you want all that to eventually kind of get integrated together, right? I mean, like it does. Depending on the exact details of the network, there is some spatial information that's kept, because of the way that you aren't mixing at lower layers, like pixels that are far away, but you eventually do. And so, yeah, you eventually kind of need that to like compress that information, and this allows you to do compression in a way that provides a bit more insensitivity to exact details of the pixel values. Yep, good question. All right, so there's more of this kind of math to be able to say, like, what will the outputs be depending on the inputs. I'm going to skip ahead because we need to move on to the next lecture. I think that's the end. Yeah. As always, there's let's see. All right. There's if you go into the files for these slides in Canvas, there are some links that you can follow and you can play around with some of the cool tools in there to kind of demo these ideas. So do follow those to learn a bit more on your own. Okay, we'll move on to Lecture 8. We're going to talk a bit more about optimization. And this is going to be basically like the last of our sort of like intro to machine learning sorts of lectures. All right, so we've been focusing on gradient descent, stochastic gradient descent. Here's plain vanilla gradient descent. We estimate our gradients, and then the gradients of our loss with respect to our weights, and then we update those weights with some hyperparameter that we call the learning rate, and here it's written as a step size. And we're just basically taking small steps that are guided by the local gradients here, wherever we are, whatever the parameters are right now of our model. We compute gradients, and we look for the direction of steepest descent, and then we take a step in that direction. Okay, and in general, this works pretty well. It converges to local minima depending on where you start. It's very dependent on things like the step size, but as an algorithm, it's simple, and if you have plenty of compute and plenty of time, you should be able to land right, smack dab in the minimum, the nearby minimum of your loss. However, we can do better. We can do better with than just plain vanilla stochastic gradient descent. Now, let me say that I'm going to go through like a bunch of examples of like different types of stochastic gradient descent that are used in training neural networks. However, it's still the case that stochastic gradient descent itself is used to train neural networks. Usually not just like just absolute plain vanilla. There's something we're going to talk about right away here called stochastic gradient descent with momentum, and that's used quite a bit, and it still is kind of the workhorse here. So don't think that as I go through this lecture that like whatever optimization scheme I talk about at the end of this lecture has got to be the best because I built up to it, right? It turns out that you can still use stochastic gradient descent, fairly successfully, especially if you add to this a momentum term, which we're going to talk about like right now. But yeah, okay. So stochastic gradient descent. So remember, this is just gradient descent, where instead of computing the gradients using all of our data, we estimate that gradient by computing the loss with just a subset of our data, which we call a mini batch or just a batch. and then we compute those gradients, and we use that as an estimate of the direction we ought to go to reduce our loss by changing the weights. Okay, so what are some problems with stochastic gradient descent? Well, here's a question that is, we can try to answer together. So what happens if you're just doing kind of plain vanilla stochastic gradient descent if your loss function, is really steep in one direction, but really, shallow in the other direction, right? It's kind of like this really weird narrow bowl. I'm talking about two directions. I mean, this could happen in many directions, right? But it's like, it's like really steep. Will bring you down to, in one direction, really fast, really steep gradients. So we have the possibility of really reducing our loss, in that direction by walking down those gradients. But in the other direction, it's really shallow, right? Like that gradient is really is really shallow, meaning we won't reduce the loss much when we take those steps. What do we expect to happen in this case? What kind of like dynamics would this have? Yeah, like what problems could happen?
You could like bounce between the two.
Like bouncing around, is that what you said?
Bounce between the two steep walls.
Yeah, bounce between the two steep walls, yeah. While we're still trying to make some progress in the other direction. Yeah. Yep. That's good. Other thoughts? Any other problems there?
Get stuck in like the flat part.
Yeah, you can just kind of get stuck there while you're bouncing around in between. Yeah. Yeah. Right. So, if your loss function is like this, there is a way to think about this in mathematical terms, which is known as a condition number, and the condition number for a function for a surface like this, you would calculate as the ratio of the smallest singular value to the largest singular value. Now, or sorry, other way around, largest to smallest, and this is just capturing this idea of like, very steep in some directions, very shallow in the other. And there's not really a whole lot there to be stuck on, although you could theoretically compute this and decide if you've got this kind of problem or not. But what happens in this case, you've all basically already said it. You're gonna, if we're just kind of naively taking steps that are like where the step size is kind of uniform for each of the directions, then we'll be making we're making slow progress in one direction where it's shallow, the gradients are shallow, and we'll be bouncing around a whole bunch in the other direction where the gradients are steep. Is there a problem with this? What's wrong with this? What is the problem with this? What's that?
Slow.
It's slow. Yeah. Yeah, it's slow. That's the only problem with it, really. Like there's a much more efficient way to get to that, to get to your minimum, than just bouncing around all the time. And like in general, like even this will converge. It's just that it will converge. It'll take a long time, and we are interested in efficiency because these networks can be huge, right? And we don't want to. We want each gradient that we calculate to be meaningful in terms of improving our loss. Well, decreasing our loss. So this is problematic. What are some other problems? Plain vanilla. So what happens at local minima? What happens at saddle points? What's a saddle point? I mean, I've seen this in math or engineering or something else. It's like, this is saddle point right here. What does this have?
Maximum in one direction, minimum in the other.
Yeah, so you have this, so in a saddle point, you have some directions in which your gradient, is pointing upward, and some that it's pointing downward, right? So so this is a kind of equilibrium in some sense, like this is an equilibrium, this local minimum, but all the forces are sort of forcing you down into here. And at this also is an equilibrium, but it's unstable in the sense that while some of the directions are forcing you down, other directions are forcing you further down. You'd go away from it if you stepped in that direction. So another way to think about this is if you compare these two, we're trying to get to a local minimum. Although if there's a global minimum, this is kind of problematic. If we are kind of near this, and we are over here on the loss surface, and we're sort of stepping down into here, we may get to here and sort of be satisfied because like it looks like our algorithms converged. But really, we could do so much better if we just took like a small step on to the other side of this, and continue to descend down to an even lower local minimum. So this isn't necessarily just a problem with stochastic gradient descent. It's a problem with first order optimization schemes. First order meaning we're just using like first order gradient or first order derivatives. So gradients to as our signal for which ways to go. But yeah, we can get stuck. We can get stuck when we could do better. This is also the case. This actually is beneficial most of the time. This bit of noisiness, it turns out, it's like a regularization term, like I mentioned. But our mini batches could be so small that really it's completely noisy. So what are some ways to overcome these kinds of things? I'm just going to move us along so that we don't get stuck again without having gotten through all the slides. So here's the first idea: stochastic gradient descent with momentum. Okay. So momentum is it's a physical idea. We're just kind of borrowing some ideas from physical systems, and using the words there. So we can think of like our loss function as being some kind of energy, right? We're trying to minimize that energy, and momentum is something like we can think about that movement as we're moving towards these areas of local minimal energy, as having a kind of velocity, and the idea of momentum is that we want to like take advantage of that velocity and use it, kind of like remember it basically. Like we want to when we're taking steps, we want to be influenced by the steps that we took before. This is like the notion of momentum, is that we're kind of moving in a particular direction. If we have some mass, we've got some velocity, like there's momentum. Like we will tend to continue to move in that direction. That's the idea here. So in plain stochastic gradient descent, we're just taking these steps. But when we add momentum, we actually are tracking two terms here. One is a velocity. We call it velocity. It's indicated by this variable v here. And what is it doing? Well, it's got the gradient. It's got the gradient term in it. But notice what we're doing is this velocity term is going to be our gradient plus the previous velocity here, right? So this is t plus 1, this is t. And this rho is typically something between 0 and 1. And so what's happening here is you're saying, okay, this is my gradient, this is telling me like locally what's going on, but this right here is telling me something about like how I've been moving in the past, right? If you think about like iterating this, we start at t equals 0 when this is 0. So t1 is just our first gradient, but then our second gradient is going to be a sum. Sorry, the second update, I should say, is going to be the gradient wherever we are now at the loss plus some fraction of the previous gradient, right? So if like it was pointing, it's pointing in this direction, and then we took a step in that direction, and now it's kind of pointing in this direction. We now have the sum of that gradient and this gradient, which is going to give us something more like this. So it sort of tempers it, and the fact that we're adding in, it's a fraction, it's like this rho is something between 0 and 1, means that if you think about like iterating this over and over and over again, we're going to get like in V, so for V3 here, we're going to have rho squared of V1, rho of V2, and then our current gradient. If we do it again, we're going to get the series where we're going to have rho to the to some power times a previous gradient. And because rho is going to be between 0 and 1, as we increase the exponent on that number is going to get smaller and smaller and smaller. It's going to exponentially, like that, the memory of that gradient, its contribution to the current velocity is going to get smaller and smaller and smaller. And how fast it happens depends, of course, on the value that we choose for rho. Okay? So we have this term, this velocity term, that is just, it's this like linear combination of all of our gradients with some factor that is getting smaller and smaller and smaller depending on how long ago that gradient was calculated. Like how many iterations in the past that was calculated. Okay? So that's that. And then when we do an update, instead of doing an update with the current gradient, we do an update with this velocity term. So it looks exactly like this, right? It's just that we now use this combination of gradients instead of just the local current gradient itself. Anybody have questions on sort of the math of this? I mean, you can also have questions on the y of this. We'll talk a bit more about that in a second. But yeah.
Shouldn't we take an average with rho VT of previous and gradient of loss?
Like when you say average, like this was like a 1 minus rho or something like that?
No, I mean divide this by 2, for example. Divide the whole.
You could do that. That would be like, it would be a bit like having, rho equal to 1, and then you'd scale it. You could do that. What are the differences between what you've said and this right here? So like, how are you weighting previous gradients with the current gradient? Say it again?
He's doing it equally.
Yeah, so, at
Kind of normalized.
well, at the current step, you are like if you were to do that with half here and half here, then that would be giving equal weight to the current gradient and then all like the velocity, all the other gradients that kind of came before that. This makes a choice not to do that, but to let this be weighted greater and this be weighted less. Now, I think one thing you are saying is something like, well, don't we get kind of like more than one gradient here if we do it like this? And the answer is yes, but you also have this learning rate out here, which sort of, in some sense, absorbs that, like those kinds of considerations. Like, you may need to kind of like, to get dynamics that are like on the same scale as the SGD, you'd have to maybe change that learning rate. But they're all hyperparameters, both alpha and rho, so we get to choose those however are best for learning. So yeah, so I think like what you're thinking is like is a good thought, and while it's not explicitly here, it's actually captured here by having that additional parameter to set.
And I was going to say also because the gradients, yeah, they'll say they have all about the same magnitude, but they'll be all pointing in different directions.
Right.
And so they won't necessarily additively keep growing and growing, so they might just not.
Yeah, I mean, yeah, so they could cancel each other out, that's right. And yeah, so like, if you think about that example, we're kind of bouncing back and forth all the time. You'd see like a lot of cancellation if you just kind of took all those gradients together. Although when you start with this, you're not going to have that bouncing around anymore. You're going to have maybe initially have some bouncing because it kind of has to warm up and get kind of a gradient direction. But yeah, you're right. Like these things could cancel out. And that's kind of the point. Is if you have some sort of really big change, you know, like balance that out with what's happened before, you know, to give you some kind of memory of like what the loss sort of looks like nearby. So yeah, it's good thought. Okay. So these are typical values for rho. Like I think if you go open up PyTorch right now and you go find the SGD optimizer, they don't have an SGD and an SGD plus momentum. There's actually just a parameter for the momentum, and by default, I think it's actually set to 0.9, if I'm not mistaken. And like this is like your default optimizer in PyTorch. So stochastic gradient descent with momentum, with that rho being 0.9. Yeah. So let's see. Let's take a little. Let's. Oh yeah. So really quickly, just to say, we could have formulated this differently. Notice when we were doing this, we were just adding up all these gradients. We could have had this be the case where we're actually just like subtracting all the gradients. Like we can put the sign here at the velocity. In which case, all we have to do. Oh, and that learning rate term. This would be a little bit more like kind of like you could maybe think about the balance between alpha and rho, kind of the way that you were in this case. If we do that, then we just need to make sure that we add that term, but they're equivalent. You can the two are equivalent in terms of the dynamics you would see in training. All right. So, what does this look like? Well, it kind of looks like this. Instead of doing all this back and forth right here, we do start to move in this direction. But depending on our choices of alpha and rho, what we hope to see is instead of doing this back and forth, that we really quickly start to sort of move through like an average version of what's going on here, because we are forcing ourselves to kind of stay close to where like move in directions similar to what we've moved to in the past. And you can, I think if I click on this, where is it? I can't, that's weird. I think you can see this in like a, what? Nope. I don't know why I can't play it. We can definitely, we're going to play it, hold on, let me just make sure we got this. We're going to see all these in action. Okay, good. So we're going to see a bunch of these different iterations, and we'll see them all in action in just a second. Okay, so SGD plus momentum. What does this look like? We're keeping track of two vectors, a velocity vector, and then our local gradient, and then the actual step, the direction that we go in, is a combination of those two, depending on rho and alpha. There is a related momentum idea called Nesterov momentum, which instead of calculating the gradient at where we are right now, it actually calculates the gradient as if I had taken a step in the direction of the velocity, and then combines the two. So this is like, there's a whole bunch of optimization schemes known as look-ahead schemes. This is one of those. Nesterov is an option that you'll find in every single deep learning optimization framework. Sometimes it's used, but more often than not, you just see kind of plain old SGD plus momentum. What this looks like here is, this is your update rule. So it's very similar to what we saw before. but what we're doing is we're, instead of computing the gradient at the values of our parameters right now, we actually add to that the velocity term discounted by that factor rho, and that gives us a slightly different gradient, and we step in that direction. So you might say, why is that any good? Well, why is any of this any good? If it works, it's great. Actually, numerically, look-ahead schemes have like better numerical properties in terms of like guaranteed convergence and things like that. But in practice, it doesn't seem to be any different usually than your standard momentum terms. So, but now you'll see Nesterov momentum a lot. It'll come up in papers, special order papers, and now you know what it is. So very, very similar to momentum, just which gradient we use is different. All right, I'm just going to get through that. So next, Adagrad. So this is now something different than what we've so plain vanilla stochastic gradient descent, and then these various momentum variations for SGD. All kind of look very similar. And in particular, they are not they're not too different from stochastic gradient descent in the sense that they're not really paying attention too much to the sizes of the gradients. The idea of momentum sort of allows you to take into account, the directions that you're tending to go with your gradients, which can help when thinking about this, this ill-conditioned loss surface that we have. But it's still not really thinking too hard about the size of the gradients in each of the directions of our surface. And Adagrad is really like the first algorithm we're going to look at here, or optimization scheme we're going to look at, that does that. And so, what do we have here? Well, we compute gradients as usual, but now what we have is we're going to keep track of something else, and this is now the square of the gradients element-wise. So we're going to compute a gradient, and then we're going to compute the squares entry-wise of each of those, each of the entries in our gradient, and we're going to sum those up into one vector. So like this plus equals means whatever, think of it as starting at 0. The very first iteration here, the grad squared is just exactly the entry-wise square of the gradient vectors. But the next time around, we're going to compute the new gradient, and we're going to compute its entry-wise squares, and we're going to add that vector to the previous vector, and so forth. And then, what we're going to do is we're going to do what we've been doing, where we're going to update our weights with the gradient. This is the minus equals, so we're subtracting off this, the gradient of the weights with the sum learning rate. But we're going to do this other kind of weird thing. We're going to divide, and this is all entry-wise, we're going to divide by the square root of the sum of these squared gradient entries from all the other iterations that we've done so far. And then there's this thing here, and that's just to make sure that if this happens to be 0 or very, very small, that we don't divide by 0. That's all that is. So that's kind of weird, right? So what's going on here? What's happening? Somebody say something about what's going on and what it might.
Function of grad squared, is it a scalar or?
It's a vector. It's a vector. So these are entry-wise. So dx is a vector, this right here is an entry-wise operation. So we're getting another vector where we've just, we've taken the ith entry is just the square of the ith entry into x. And then we're adding that to, we're cumulatively adding that to all the previous gradients that we've computed so far.
But where does it get summed together?
Right here, plus equals. So it's a Python.
So then when you divide by the grad squared, is that also still a vector in parentheses?
Yeah, everything here is entry-wise. So the square root is happening entry-wise. And then when we do this division, so this is a vector, right? And then this is going to be a vector. And this division is going to be an entry-wise. So we're going to divide the ith entry of this by the ith entry of this. Yeah.
So it seems like this would slow down like your rate of learning like pretty fast, because if you keep adding the square of the gradient, like the square is always positive, the grad squared is always increasing dividing by it. So it seems like
Yeah.
this like continuously like slow down the learning.
Yeah, so it can slow it down if the thing you're dividing by here is greater than 1, right? It's going, think about that as like, in that particular direction, it's reducing the learning rate. But you can have the opposite effect if it's less than 1, right? You're right that it's non-negative. You're right about that. But if it's less than 1 and you divide by, you're actually making it larger, right? So, say more about that. What is this doing?
Well,
Now, I think what you're saying is something like the following, and you're right. Eventually, if we keep adding if we keep adding even small numbers, like maybe that will get to something.
Like eventually it'll go above 1, and that's never
It actually doesn't have to, right? Like we can have a series or a summation, an infinite sum that converges but doesn't converge to 1. But that would have to be, certain properties would have to exist about that. But what is this trying to do? Yeah. I mean, this may not be like the best way to do it, but if it's steep, if you have a very steep loss function in a particular direction, you're going to be dividing by a large gradient, right? Even the square of that. You're going to eventually take the square root of all these sums values here, but if that's very large, you're going to be dividing by a large number here in that direction only. So think about that as like modulating the learning rate in that direction. It's actually decreasing it so that you take a smaller step size relative to the other directions in that particular direction. And if it's the other way around, where it's very shallow, we have a very small gradient, then squaring it makes it even smaller. You got to think about it being less than 1. And you're going to add it to what's come before, but let's assume that all of that and the square root of that is going to be less than 1. Then we're going to be dividing by a small number, which will relative to the other directions will inflate that learning rate. And so we're modulating the learning rate in the different directions by dividing by this kind of weird term right here. Now eventually, I'm kind of with, I already forgot your name, but I'm with you in the back there. We're like, eventually all these numbers are going to get above 1, and we're going to be like, dividing by numbers larger than 1, and that's going to reduce this learning rate, and then it will, every time after that, we'll reduce it even more, so that this is like naturally kind of slowing down the learning as as the iterations go on. That could have some kind of nefarious effect on us, right? That could actually stop us early from getting to our to the local minimum. But if we haven't chosen the parameters so poorly, this might have the benefit of when we get near to a local minimum, that we're actually like slowing down at an appropriate rate, so that we don't like overshoot that minimum. I mean, the lower gradients are gonna make sure that happens, but when we're close to a minimum, right? Like all of our gradients are going to be small at that point. But yeah, what happens there depends on our loss surface and on our choice of learning rate and so forth. But the idea of AdaGrad is that we're getting these, we're modulating the learning rate per direction depending on the steepness of the gradient. Yeah.
So if it's steeper, it slows it down, and if it's shallower than 1, it speeds it up. But then when we get to the 0, when we get to a flat spot, it'll speed it up, right?
Right, except that by that point we've gone through a lot of iterations. And remember what we're doing is like we're always, this is like a cumulative sum here. Like every iteration you add to it whatever, like the squares of the entry-wise square or element-wise square of the local gradient. So that's just accumulating. So it's more, I mean, again, this is what I was saying, it depends on the exact, details of the loss surface and your choice of learning rate and where you start and all that. But in general, by the time you're getting, you've taken that many steps, you've probably already gone above 1, and you're like slowing down. And then those gradients are small, so they're not changing. Or you're going to add something to it, but not very much, and then you're going to take a square root of what you've added to it. Uh-oh, this is always the sign that says you're taking too long. Yeah, so like you're going to add something to it, but not that much. So like that factor that you're modulating by won't change a whole lot at that point. I mean, it's not like a perfect story, but it's kind of like that.
It seems like if you're kind of early in your iterations and grad square is still small, like this could cause you to overshoot a local minimum, which would be a good thing because you're down the other side and keep going. But if you're later on and grad square has gotten pretty big, then the function's just gonna stay in the next local minimum that it encounters. So it seems like you're kind of relying on grad square to grow at the right rate, so the
Right.
minimum to start at, so
Right.
that's a true one.
Right, and there's no guarantees around that. So it's good. Yeah, it's like this isn't perfect, but it is a way, and it will give us now. It's going to be the kind of inspiration for a bunch of other ideas like this that are taking into account size of the gradients to modulate the learning rate in different directions. Okay, cool. We better keep going. I am always behind. Yeah. Of course, we already answered all of these. Okay. Other versions of this kind of optimization scheme. So here's AdaGrad again. So here's something called RMS Prop. And it's similar to AdaGrad, but it's also different. And some of you might have already been thinking, why don't we actually do this already? But you didn't say it, so now you can't claim that you created RMS Prop yourself. But what's the change that's being made here? Obviously it's being outlined, but what's happening here? Like, did anybody feel like it just was wrong to just keep adding the gradients up without paying attention to how many gradients you'd added or something like that? I mean, you were Mr. I'm averaging all of these things in the last one, right? You didn't. This didn't seem to bother you this time around. Maybe you thought, well, I won't ask that question this time. I don't know. Yeah.
Yeah, we just added a discount factor. So.
Yeah, and it's not just a discount factor. It's actually you're getting a weighted average this time, which is unlike what we had before in momentum. So you have some sort of discount factor, it's called the decay rate here, where the contribution of previous grad squares is going to just decay at an exponential rate. But unlike in momentum, where we just add whatever this term is over here without changing this or without doing something to this value, we actually here have 1 minus this discount factor. So it's actually a weighted average, right? Because since these two weights add to 1, we're getting this nice balanced weighted average between the sum of all the squared gradients that have come before and then our current one. And then we do exactly what we did before. We take this, we take the entries of this squared vector, we take the square root of it, we divide by it, and now we're modulating the learning rates again. And it's another possible optimization scheme you can use. This every once in a while kind of shows up. Interestingly, all of these optimization schemes have a paper that was written about them, and you can go like cite the paper. This is the one exception. There's a well-known lecture by Jeff Hinton where he introduced this and called it RMS prop, but it was just in a lecture, so there's no paper for it or anything like that. It's just like you have to just kind of know the lore, the history of deep learning, the progress of deep learning to know that that's what happened here. So it's called RMS prop, but you can't go look up the reference for it. You just have to kind of know that it sort of showed up one day in a lecture. Okay, so you could do that. I kind of like it. It's kind of nice because it's got this like balance between them. But should they be balanced? Does it matter? I don't know. Like, is this going to solve these problems we were talking about before? Like, is it going to be better tuned to getting us to like land nicely at minima? I mean, who knows? Yeah, that's right. Like in general, no. There's no guarantees here. Okay, so what we're going to do is we're going to look at. So here's some sort of simple loss surface in 2 dimensions. We're going to be starting at this initial point here. We're going to see the trajectories. So this star right here is where actually the local minimum is in this basin. These lines, these contours are contours of equal loss, right? So this is like the bluer it gets, the smaller it's getting. This is kind of reverse of the color scheme we had before. And then what you're going to see is you're going to see what the effect. We're going to keep the learning rates the same, but what's the effect of using stochastic gradient descent to optimize our weights to get to here? What's the effect of adding momentum to that? This is our Nesterov momentum. Then we have Adagrad, we have RMS prop. There's one other here that we haven't talked about, Ada delta. That's another version of this, and we're going to see the dynamics of these as we run iterations of these various types of gradient descent. I think this is just going to play repeatedly. Okay, so all right. So take a look at this a couple times, and then start making some comments. What you see.
The best one is RMS.
What's that?
The best one is RMS because it's faster than others.
Okay. So there's one vote for the best one is RMS prop. Anybody want to argue with that?
Oh no.
What's that?
I think that's Prof. I was going to say that that's Prof. Because it does look ahead and it avoids getting into that zigzag pattern of those down there.
Yeah. Yeah. These are great thoughts. You can imagine there's actually really no right answer. I'm just going to get you to just comment and we'll see what comes out of it.
Definitely makes SGD look really slow.
Say it again. It makes sense that what?
It makes SGD look really slow.
Oh, SGD look really slow. Yeah, very slow. Why is it very slow?
Same step size every time.
Yeah, this is taking the same step size every time.
So are the learning rates the same for all of these?
Yeah, the learning rates are the same on each one of these, exactly. So it's kind of unfair to SGD. You actually could probably tune SGD like a little bit, like pick a different learning rate and find that it like converges faster than what it is here. But So it's maybe not exactly like a totally honest story here, like boo SGD, but tuning learning rates is a real problem, and methods that actually sort of tune the learning rates for you by modulating the gradients, or by using the gradients to modulate the learning rates are really nice in this way. That they sort of, your optimization is still sensitive to it, but far less sensitive to the actual choice of learning rate, because you can, it's adapting itself to it.
Is there an explanation for why the per parameter methods take a super different route from the based methods?
Like these ones here, like
Yeah.
blue, yeah, they do. So let's just kind of like walk through it real quick, and I'm going to give myself 30 seconds to do it, because otherwise we'll take 10 minutes. So, what's happening here with the other? Let's start with these other ones first. What's happening here? There's just momentum, right? So, like, if you think about what the gradients are going to point perpendicular to the lines of constant loss, right? So, they're pointing in this direction, and they basically, all the gradients are kind of like the same over here in this part of the loss. I mean, it starts to get shallower because the contours are spread out, but they're all pointing in the same direction. So these ones that use momentum, like a lot of momentum is building in this direction, right? And then, like in some sense, they totally overshoot this, right? So they go way over here, and it's not until this loss is starting to decrease again, where it's like the gradients are starting to like point in these other directions, and it's like, oh yeah, I guess we better go this direction now. So that's what's happening with those. And so these other ones, like just think about Adagrad. We're taking these gradients, and then we just kind of keep adding up the squares of them, right? So they're all kind of pointing in the same direction. So they're all, like if they're large, if it was large here, it's large here, and so all of a sudden, the effective learning rate in this direction is really being decreased, right? So we don't change as much in this direction. Now at the same time, the gradients that go in this direction are really small when we're over here, but all of a sudden when we get down here, now they start to kind of build up, and it's going, so it's really small. It's saying, hey, moving this direction is advantageous, or well, it's just relative to the other modulated learning rates, they're larger, and so you see larger step sizes in that direction. And then it starts to build up in that direction, and then everybody slows down when they get close to the minimum here. So that's all. It's just the fact that like the gradient in those directions is becoming really large, and we're dividing by it. So effectively, we're reducing that learning rate in that direction. That's really all it is. Other thing you should notice is that like there's a lot of similarity between them. I mean, and this is in general like what you're going to see is like things that kind of look like each other are going to kind of perform similar to each other, and it's really just like ends up being a choice. Like your favorite. You just like if you're always in an RMS prop, you're like, yeah, let's use that. That's great. Okay. So there's one more we want to talk about that's quite interesting. That's in this family called Atom, and this is actually this is probably the go-to for like when you're starting off for most projects that people do. You start with Atom, and there's some variations on Atom. We just can't get into every single variation, but Atom is it's probably the one that people start with most often. And then when you kind of get some feel for what's going on, if you really need to eke a little more performance out, people then go back to stochastic gradient descent with momentum, and you can usually get a little bit better performance. It's just like one of those weird things that you learn as you start to do a lot of this work. So this Atom is like, hey, if adding the squares of the gradients was a good idea, let's do that, and then let's also add in what looks like a moment, a first moment. A momentum term, and let's just let's just do all that all at once and see if that does any better. Now this says almost, this is not quite right. This kind of builds up your intuition of what you maybe would expect to do, right? So what we've basically done here is combine these the momentum term and this squared gradient term into one optimization scheme, right? So instead of this being gradients here, the local gradients, we have now a momentum term that we're tracking. It's almost exactly the same, as we saw before, but this time it's you have this weighted, this balanced weighted sum, and you have the same thing here. So this looks like RMS prop, right? It's got that balance weight of these two hyperparameters, beta 1 and beta 2. Okay, this is almost Adam. This kind of makes sense, right? Like if you're just kind of iterating on these ideas, like this would be one of those that you tried if you already had tried momentum and RMS prop, right? And this actually works pretty well. Let's see, do we have the time to do this? So okay, so I'm going to say this because it's important to what comes next. So when we say this is almost what Adam is, it's because it really is, except for the fact that you have this problem when you warm up. So what does happen in the first time step? If we start with zero, so we're calling these moments now, instead of like gradients and square gradients, we're just going to call them first and second moments. This has some grounding in, inertial physics and statistics and things like that. But anyway, we'll call them first and second moments. So what happens when we start off in the first iteration? So this is 0. So we just have this term right here, and it's going to be like, we know this is 0, so this is going to be down weighted by a factor of 1 minus beta 1. Okay, and same thing's going to happen with the second moment too. Because we have this weighting, this is going to be down. This be down weighted slightly. Whatever beta 1 or 2 are, that's going to be down weighted. And you can see how through a couple of steps that's going to persist, right? Like if this actually ends up being kind of small, then it takes a while for this to sort of build up to be like on the same order of magnitude as the other terms. Okay, so that adds a kind of bias as it's thought of or as it's called in this optimization scheme. So we correct for that bias. And the way we correct for that is we divide by 1 minus beta to the tth power, meaning t being tracking the number of iterations we've taken. So at t equals 1, this is literally 1 minus beta 1, and we divide by that, and we have just the gradient, right? And same thing here. This is 1 minus beta 2, so we're dividing this term by this, so we just have the square of the gradient. And then as we continue to go, we're going to have this balance between here and here that will exist, but we continue to divide by the square, or by the not the square, but by the power of 1 minus beta 1 to the power of t, the number of iterations for beta 1 and beta 2, and so we continue to divide by those. So what's happening here? So I sort of didn't say it already, but beta 1 and beta 2 are both values between 0 and 1. So as we increase the number of iterations, what's this value going to? Both of these values, what are they going to? 0. So 1 minus that's going to 1. And so we're dividing by something that's closer and closer to 1. So as the iterations increase, this operation sort of is doing nothing, right? It's barely changing things. So it looks like what we wanted before, but early on, this has a big effect in terms of balancing the effect size of the first and second moments in this, so that we don't have this sort of like slow warm-up period. And now that's Adam. So it looks like what we had before, like combining momentum and RMS prop. but then we add in this kind of bias correction, and that's the full form of Atom. And that actually works pretty dang well, actually. And again, most people start with this optimizer when just starting into a new problem. And the main reason being is that it has this property where it makes it makes the learning dynamics less sensitive to the specific choice of the learning rate. Really quickly, this can adapt to it by changing the sizes of the gradients to get to relative to the other ones and to get you good learning dynamics. Right. So we've got just a couple of minutes. I still have a couple of these slides to go. I'll just make mention of these, and we'll talk more about them as we learn to train these actual large networks. So this question is like, what's the choice of learning rates? So that in general is one of the most important things to figure out, to get the learning rate and the batch size figured out as hyperparameters for training neural networks. And it's totally an art. There's not really like well, here's the best way, And so what do people do? Well, you choose optimization schemes that kind of correct for this already, and that helps a lot. But you can do other things, and these are known as learning rate schedules. So we don't have to keep a fixed learning rate the whole time. There's nothing saying that we have to do that. In fact, it's almost always to your advantage to have some kind of learning rate schedule. And the way that these usually go is that they decay the learning rate over time. And if you think about it, that makes a lot of sense. When you're starting off, wherever you randomly initialized your weights, you're starting your learning, you kind of want to explore the space a bit, right? Like you want to have a large learning rate and kind of explore the space and see if you can get yourself into a place that has like a large basin where you're starting to be attracted to in terms of like the dynamics of learning. But as time goes on, once you kind of explored that space a little bit, and you got yourself into a nice basin, you want to not do so much exploring, you want to exploit where you are. And so that exploiting means that we take smaller and smaller steps as we kind of like look for, we look for directions on the loss surface to get to even lower and lower loss. And that's what the learning rates schedulers do. There are typical ones. In fact, well, this is really common step decay. So it's like you either have it on a fixed schedule or you pay attention to your gradients. And as your loss, if your loss isn't changing very much, then you just like drop your learning rate by a certain factor, and all of a sudden your loss starts to decrease again because you're allowing yourself to kind of get into like smaller regions, or to get into narrower regions of the loss function, and that actually works quite well. There are these other ones that just decay over time. Nobody really uses these anymore. Actually, what you see now are cosine decay rates, where you basically just like linear and cosine decay rates, where you choose how many epochs you're going to train for, or just number of iterations, and you just literally, like on a cosine, start at like the top of like a cosine and kind of work your way down to the bottom of the cosine to like as like a factor from 0 to 1. And that actually ends up working really well. You see it all the time these days. Linear ones as well, linear decay. This is what the step decay will often get you, is just like lower and lower loss every time you step. The one thing that we're not going to be able to cover today because of running out of time are second order optimizations. So we talked about this kind of briefly the other day. You can use not just the gradient information, but information about the curvature locally to tell you something about how far you should step. This also allows you to kind of modulate, the step size you take in certain directions. There are great optimization schemes for this, like Newton's method and things like that. But the problem that we already talked about is that these now, the computational cost grows in the number of weights that you have, right? Squared for Hessian, for the Hessians, for the second derivatives, and then of course when you invert that, you have another order of n that gets multiplied there. So this becomes a huge problem. There are other optimization schemes that can kind of that sort of get around some of these things, like a quasi like BFGS, which gets around like inverting, so you approximate the inverse of the Hessian, and other versions of this. And actually these work really, really well. Like if we could calculate these, we would do it because they actually work super well. But they just slow everything down so much that it's not worth it. We just do first order optimization. So in practice, start with atom. Usually, if you need to eke some more, after you've kind of got atom tuned well, you kind of understand the dynamics. You often, if you need a little more performance, you often go back to stochastic gradient descent plus momentum. And if you can afford it, but you never can, you can do some second order schemes. So that's it. Thanks for sticking around for a few more minutes. And I'm going to be here for a while to answer questions. Homework's due tomorrow. Good luck. I'm sure you'll do great. Hi. It's related to your code. Yeah. It's definitely your code because it works otherwise.